out of our heads. Reasonable fenestration. We're going to talk a little bit about windows, where and what kind. Continuous exterior insulation. We are going to emphasize that. And renewable energy, along with a few additional design considerations too. And also we want to emphasize that Jennifer and I also, we talk a lot about cohesive systems and building within a system. Like we put a car together, that's a system. When we spend $50,000 on a car, we spend 2,000% more on a house, and we don't always think of it as a system. We take a part off the shelf that doesn't play nicely with 4 or 5 other parts. You'd never accept a car that didn't work as a system, but we have a tendency to accept a house that doesn't work the way the system should work for a house, and we pay a fortune more for the house than we do for a car. Also that, you know, all electric is one step towards a decarbonized world. Within that system is renewable energies and a converted grid. And within those systems is helping to reduce the loads of our buildings through practices we already know. So, you know, reduce, reuse, recycle, it's kind of, that theme plays well here as well.
Okay, as I'm speaking, you guys can tell me if you're going to be able to tell that I was actually born in Wisconsin. Because after I listen to Michelle and Mike talk a lot, I start to say my O's differently. but I pretend that I'm really from California.
Jen, that makes sense. I'm from Minnesota, so you sound like a local to me. Aha.
I know, but I moved to California when I was really, really little, very small. After I learned to eat bratwurst and drink beer. Okay, so when we talk about all electric buildings, a lot of times we as architects or builders or designers, if we're in the trades, we might understand a lot about buildings and thinking, okay, going all electric's not really a big stretch. But we're finding that a lot of us, when we talk to our clients, the homeowners, the developers, some of the builders, they are not familiar with all of the things that California is doing to move towards a reduced carbon footprint and move towards more and more renewables as being part of the energy grid. And to take advantage of those renewables and to take advantage of an electric grid that is less dependent on fossil fuels, it makes sense that we would use more and more energy efficient equipment that is all electric. So to make that easier, under Title 24 Energy Code, now if you have an all electric project, it's going to compete or kind of calc out the same as a gas project. So it no longer matters if your property has gas on it or electric on it. You can choose whatever fuel you're going to use on the project. Just as a reminder, all the low-rise residential new construction, a certain amount of PVs is required. And the other thing that I think all of us don't realize in being in California is that all this all electric technology has been field tested already really throughout our country and in the world. So I lived in Denmark for some time. There were heat pumps everywhere. That's all you had. That was 20, 30 years ago. Back east where Mike's from, where we all lived, there's heat pumps that have been used for the past 10 years that are very efficient. And Mike's gonna hit on that. So California is not, we're not the guinea pigs. We're getting to take advantage of things that have already been figured out.
And along with those concerns, a few things we'll point out that we often get questions on. Power outages. Most modern gas equipment, even though it's gas equipment, still needs electricity to operate. Cost to build is always a topic. My background is actually economics and finance and linguistics. Jennifer's is science and computer math Jennifer?
Yes.
Yeah, so, and then, you know, I'm still banging nails. I was in a trench this morning before running to the office to teach this workshop. In the trench I was in was the electric trench that we're running from the street to the house. And we're running that to hook up our 3.6 kW PV system, which is a total of $9,400 for our entire PV system, 100% of the load of this house. $11,000 was the quote from the gas company for the same amount of length to run the gas line from the driveway corner to the house. So our entire PV system is $1,600 less than the cost of just trenching the gas line from the driveway to the house. So cost to build, if we look at big macroeconomic pictures, I think it's cost effective, if not cost savings, because I find it's a lot easier if you think about it as a system. Cost to operate, so we're not talking about electrical resistance, we'll talk about induction and heat pumps. Gas is still used to make electricity. 84% of California's gas is imported, and along with that import, we have large leaks of methane before we turn the methane on inside our house. And I might have this number wrong, but I know I have it close. I think they say if a leakage rate of more than 3% is equal to still having coal power plants firing up your energy. And I believe California's gas import leakage rate is above 5%. It's really bad. So gas cooking. We're going to dispel a few myths about gas cooking in a few videos. We've kind of been taught to equate flames to speed and control and power and skill. We'll dispel some of that.
Okay, and then just a few more points that might come up as you're talking to your clients. The EPA's linked asthma to the indoor combustion pollutants that we have inside our homes. So, you know, independent if you go electric or not, you need a lot of fresh air ventilation to counteract that. But just the fact that they have now enough studies and enough evidence to link the two and have that positive correlation is significant. We all know that there's always ongoing safety issues with having combustions inside your home. That's why you have to have CO monitors as part of the code. But the other thing is all electric buildings are easy to build, and they're actually really easy to operate. And if your clients are also concerned about future proofing, that's something California learned, and do I dare mention Texas right now is learning that, like, unregulated market and all the gas prices are continuing to go up, and it's a limited resource. So we have clients who want to future proof for that, so they're considering all electric with battery backup as a potential solution. And so that might come in to play when you're talking to some of your clients. Berkeley, yeah, I saw I saw Mike's arrow there. That's right, Berkeley banned new natural gas installation just based on safety concerns. Mike, wasn't one of the places you used to live one of the areas where the gas pipes were?
Yeah, Lowell, Mass. Lowell, Mass has had 3 gas main explosions that have basically destroyed full neighborhoods. Yeah. They had another one this year, not Lowell, but around Lowell, Fitchburg, Brockton. Yeah.
Okay, so there is definite, real ongoing discussions about maintenance, reworking. So we're not saying, oh, we need folks to be out of work. What we're saying is there is work that needs to be done on an existing infrastructure to make it safer for what is there. And in the meantime, people have the option to convert to going with renewables and renewable energy.
And that gas infrastructure is going to be around for a long time still. So no shortage of work in that field. All right, so now we're going to kind of get into the main focus. We're going to get into the 4 pillars. So the first is about heat pumps. Quick history. some of the growing pains, dispel some of the myths, how they work, where they work, and the different types of systems. We've got 3 systems that we're pretty familiar with. We're gonna try to move quickly because we have a lot of stuff to talk about. And if we tend to take acronyms out because we hate when people use acronyms, but if there's any language that people don't use, construction speak or something comes up, don't be shy about saying, hey, what does that word mean? Because we don't always speak the same language. So science, physics, math, thermodynamics, heat pumps, refrigerants, really it's just used for beer. If we think of our refrigerator, every single one of us uses a heat pump every single day. So they're moving existing heat from one place to another. A refrigerator doesn't make our beer cold. It takes the heat away from the warm beer that we put in our refrigerator, and it moves that heat, it pumps it. So the pump from heat pump is the verbal pump. So it pumps that heat out to another location. So you're not making your beer cold, you're taking the heat away from your beer. You're dewarming your beer. So that's how a heat pump works. That's actually my refrigerator too. That's my 37th birthday. 38 was the start of a new era. No more refrigerators like that. So quick history lesson. We often run into this, and I think Erica, you were kind of hinting at this. Is it your dad that's a bit old school?
My stepfather, the contractor. Yep.
Yeah, so you will often hear, as soon as heat pumps come into play, you'll hear people say, well, they don't work when it's cold. We're not putting those in. That's true of the old kind, not of the new kind. So the first generation, they were really bad. So the first generation of heat pumps, they operated at 1 speed. It was basically a boost mode 24/7. And since a heat pump is moving air from one place to another and taking air, oops, sorry, I'm running a job site at the same time and my phone's blowing up. So it's moving air from one place to another and taking heat out of that air. Well, since the old heat pumps only ran at 1 speed, which was boost speed, it was just shooting air as fast as it possibly could. And they never had the chance to gather the heat that was in that air into the system. So it was this great concept, but just a really poor design all around. So today's heat pumps are variable speed heat pumps, usually a low, medium, a high, and then there's a boost option as well. So they don't cycle. The idea is to turn it on, set it and forget it, and walk away. So they work very, very efficiently. They work less efficiently if you turn it on in the morning and then turn it off in the afternoon and then walk back out and turn it back on the next morning and turn it off in the afternoon. Just turn them on, set the thermostat, and let them be what they are. So they do not fail in cold weather. I've been using heat pumps on projects since about 2007, 2008, I think was the first time we did it. And it was one of those, once you learn how to do something that's so simple and works really well, how do you unlearn how to do that and go back to some kind of gas forced system? So we stuck with it and it's worked really well for us. And that was in New England, coastal New England. Most of our projects were right on the ocean, Cape Cod, Massachusetts. So now, great concept, better design, simpler and smarter. So like the beer, heat pumps are moving heat. They're taking heat out of something, and in this case, it's the temperature. So there is heat. This is kind of the sciencey stuff. There is heat in any kind of weather. So even 50 degrees, minus 50 degrees Fahrenheit, there's still technically heat in that air. And the refrigerants that we use today can capture heat from minus 50 degree temperatures. Still a little bit of heat that can be captured. So they're not making heat like gas equipment. So we're not, if we're using a heat pump dryer, we're not cooking our clothes like we would basically putting clothes in an oven. They're just moving heat from one place to another. And there's always heat around us no matter the temperature. Where we use them, pools, we can heat small pools with heat pumps. We can heat Olympic size pools with heat pumps. You can gang them up together. depending on how much you want and how big the pool is. You can use it for community pools. Actually, very common for community pools in Iceland, where every town has a community pool and a sauna and a hot tub area. So people don't go to the bars after work, they go to these little community pool areas. We use them for laundry. This is on the left is a whirlpool. That's a 7 cubic foot, which is pretty typical of American size. I'll be using that one in a project here. The middle one is a Bosch, which I think is a 4 cubic foot or 4.3 cubic foot. More typical of European, Japanese, Australian residences. You might find the smaller dryers. We like things big here. And this on the right is an LG model that's also a 7 cubic foot. I've actually heard that this LG model is being discontinued. But the Whirlpool is still readily available. So we use it for our laundry. Hot water. This is a Rheem Performance Platinum. That's an A.O. Smith model. Those are called, the Rheem and the A.O. Smith are integrated hot water heat pumps. So they have the heat pump on the system. You have a holding tank, a storage tank, and the heat pump on top of that tank. The Sandin is what we call a split heat pump system. So you have a tank inside the building somewhere, and you have a condenser and a fan outside the building in a different location, not too far away. This is a space pack system. We learned a lot about this as we've been looking into heat pumps for radiant flooring. This seems to be a system that people will go with for radiant flooring heat pump systems. Electric cars. So electric cars have started integrating heat pump technology, and that has to do with the fact that drive range is a big concern. Crazy. Drive range is one of the major concerns of owning an electric car, and the drive range correlates to battery usage or battery drainage. So the goals of most electric car manufacturers are to make the loads in the cars really as small as they possibly can. So I think it was Nissan was the first to really incorporate using heat pumps in the first editions of the Leafs, and now most electric cars use a heat pump system versus old cars, which would use an electric resistance system to get heat inside our cars. Space conditioning. This is a big topic and probably what a lot of people think about when they think of heat pumps. We teach an entire different course on just heat pumps for hot water, which is a lot of fun if you're into that kind of geeky stuff. But for space conditioning, there are really 3 systems. So we have a ducted system heat pump. We have ductless system heat pumps. We also have a package system, sometimes called a package terminal system heat pump. And that's often what we'd see in, like a Days Inn or a Motel 6 if we're staying in one of those, and they have that little unit underneath the window that's pumping into the house. So we'll go over to the ducted and the ductless are the ones we'll probably be using most often. So we'll give you a little insight into those. A ducted heat pump system is really not very unlike our forced air gas systems, but it's a heat pump system. So it looks like a forced air system, like our typical gas system. Locate the equipment in garages, mechanical rooms, basements. We don't have a whole lot of basements here in California, but it'd be like having a furnace inside a house. You put it in the same location, and then you'd have a condenser outside the house somewhere else, and the inside part of the house would look like a gas FAU. If you didn't know it was a heat pump, you'd probably walk into the building and think it were a gas FAU. We put that you can theoretically utilize existing duct systems in renovations and remodels. Theoretically, you should take a good hard look at the existing ducts before you choose to use them while switching to a forced air system. Probably not the most efficient way to do it, but if the ducts are in good shape and they're not too old, it is possible to do that. It's a question that gets asked, so we address it right off the bat. This is a ducted system as well. So heat pumps have what's called a concealed duct system. And we call it a concealed duct system because it's really smaller ducts. It doesn't look like a gas forced air system. It's ducted because you'd have short runs of ducts that come off an indoor unit, often located in an attic area. And those short runs of ducts would go, I don't know, Jennifer, what, 10 feet, if that, sometimes even less, into a room, into a register in a room. So
Yeah, that's right.
not very far.
The idea
so-
is to keep the ducts compact.
Yeah.
It improves the efficiency.
It doesn't look like a gas FAU system, but because it has ducts, it's called a ductless system. And again, you have a condenser outside and you have refrigerant lines running from your outside condenser to your unit inside. And they're transferring heat, capturing heat and transferring it from one place to another. So then we have our ductless systems. We always get a question about this. There is a mini split up hidden behind that bookcase there. This is to show that it is theoretically possible to conceal an indoor unit that's mounted on a wall. Sometimes people say they don't recommend doing it. I still think you can do it. You just have to think about the airflow. You can't just put it in a bookcase and then cover the bookcase. You have to think about air being able to move around from the unit. So can you guys see my arrow as it moves on the screen?
Yes.
Sometimes I have to hold a clicker. Great. So this is a piece of built-in furniture with a wall-mounted unit. And then this is actually a house I built where we mounted a unit up on the wall, up high above. This is a few years ago, and I don't remember the exact size of this. I want to say it's a 9,000 BTU. It could be that it's a 1-ton system, but this is the only heat and air conditioning that we have in this entire house, which this is about 25% of what you see there. So all we have in this house is one system. So you'd have there's a condenser, a refrigerant line runs down the wall, and there's a condenser down on the bottom floor outside. This is a ceiling mount unit. They're made to fit 16 on-center joists. So it mounts up in the ceiling. I have one here. So they're about,
He's coming back.
they're about yay big, and they mount up in the ceiling cavity. I'll be using something like that in the passive house we're building in town, 3,000 square feet, 2,500 square feet of conditioned floor area, and I will just be using one of those for the entire house. So,
Mike, with that house, real quick. Oh, and we're at like 9:33, by the way, Mike. And for that house, when you say you have that one indoor unit, I think it's important. Okay, I'm laughing. Mike uses the best visual aids. You should hold that up again so people can see it. Well, I ask you this question. That indoor unit, yeah, you say, okay, you've got just one, but it's important to point out also that you have another mechanism for distributing the heat throughout the house. So it's not just like it dumps heat in one corner of the house and then the other parts of the house are cold. It's that one source of heat. And then he has another way that's not part of the forced air system, that with leaky ducts, you know, all the bad stuff, but that uses another way to transfer the heat so that the space is comfortable. And we'll hit on that with one of the design considerations towards the end.
thanks. Yeah, that's part of the, the system we're talking about. It's building within a different system. So an advantage that space conditioning with heat pumps has, you can use all of the different indoor units on one condenser outside. So you can use a wall mounted unit, which is, I don't know if I showed a wall mount unit, but we have one hanging on the wall here. I can't turn my camera. You can use a wall mount unit. You can use a ceiling mounted unit. Different types of ceiling mount units. You could have a forced air system. Those systems can all run off one or two condensers outside the house. So you can use different types of systems in different areas of the house. The only thing you can't do if you do something like this is a quick example. We were working with a group doing multifamily units, and in our first initial meeting to talk to them about moving all electric and not using fossil fuels, we let them know that, they were going to build 3-story apartments. And we said, you could have one condenser outside. There are 1,800 square foot apartments, and one condenser can have a line set running up the outside of the wall, and there can be one unit inside each apartment. And that's very efficient. The only thing they can't do is have one apartment with the heat on and another apartment trying to run air conditioning at the same time. So you can't run heating and air conditioning. Maybe we haven't emphasized enough that heat pumps provide heat and air conditioning at the same time. So all of these units, they're not just for heat, they can run in reverse and give you air conditioning. So in our house here up on Bishop Peak, we'll have one unit providing the heat. And it's a longer story, they'll never have to turn the heat on, but we did a 20-year outlook to the climate around here and said, even though it's going to be a passive house, they might need air conditioning on some days when it's 120 degrees in San Luis Obispo, like it was last year. So this same unit provides air conditioning for us as well.
When it comes to those kind of other parts of easy, so when we think of moving all electric, if you think heat pumps, then you're thinking, okay, that takes care of your appliances, really, your heating, your air conditioning, and your hot water. So what's the other part of making this move to all electric work as a system? And we did have a comment about, VRVs running both simultaneously, yes. But on this residential scale, the equipment we were talking about, you'd either operate it all in heating or operate it all in cooling. But if you do have a more robust specialized system for big multifamily or hotel motel or office occupancy, they do have equipment where you can handle running air conditioning and heating in the building. But that's a little more robust system than the type we're talking about, today with the single family residence, small apartments, and small commercial. So the other part of making this whole package work, and again, this is a residential strategy here, is looking at your glass. What's reasonable for your windows, for your fenestration? And for the architects, just give you kind of a reminder that in California, we have different climate zones. Most of the time, the windows are going to need a U factor of a 0.3 or lower. And that's going to be true as a baseline throughout all our climate zones. And then the solar heat gain coefficient, that's the part of the glass that determines how much of the heat is allowed through the glass and how much is reflected or not allowed to go through the glass and is pushed basically back to the outdoors. That solar heat gain coefficient of 0.23, it represents having 23% of the heat in the sun allowed to come through the glass. Well, in climate zone 5, there is no solar heat gain coefficient requirement. So just as a kind of rule of thumb, we like to tell our clients, aim for about a 0.35 solar heat gain coefficient. That way it will let in some of the winter heat, but not too much. And if you're doing passive solar strategies, like you're really on purpose trying to design the house so that you are allowing the winter heat in, you can have up to 20% of the floor area facing south, and you can design the house so very, very little heat is needed. If it's not a passive solar house, then we recommend that all of the glass added up on all sides of the building don't exceed 20% of the floor area. Of course, it's just the opposite for cooling. We say lots of shade and keep your non-south fenestration below 5% of the floor area and use it for daylight egress and views. So part of that is you have to design your overhangs for sun control so that they're optimized for the size of windows you have. And we highly recommend operable exterior shades, given that our climate shifts a lot on the Central Coast between needing shade, even in the shoulder months, to needing to let the sun in during the winter time. Mike's going to give you an example of the temperature swings that he's seeing in one of his projects.
Yeah, this is actually my personal house. So, well, personal apartment downtown. So I live in a brand new apartment in downtown SLO, and you know, built to code. I think it was finished in 2018, probably. I moved in as they were tiling the backsplash, so I'm pretty sure it was finished in early 2018. You know, really pretty, nice looking, good appliances, clean counters, all the nice stuff that you'd want in a nice, cozy downtown apartment. So I love this little temperature gauge that I bought for 12 bucks off of Amazon and pretty much carry in my tool belt everywhere I go. So this is just to show you the importance of windows and the many layers of protection that they can offer a building, or that they can fail to offer a building. So, you know, I have new windows in my house. They're just Milgard, you know, code minimum. So regular day in the Central Coast, 70 degrees outside. It was 84 degrees at 2 o'clock. 7 o'clock in the evening, it was 70 degrees. So this is my southeast. This is a southeast facing window in my house, a kitchen window. So I've got my temperature gauge on my center mullion, and it's showing me that it's 72 degrees outside. I've got a huge oak tree that shades that window. I get a lot of ambient light, but I don't get any direct heat. Now, same time of day, you know, 7 o'clock p.m. So this was probably the summertime, still light out. It's 70 degrees outside, but I have this west facing window that doesn't have any protection. It's just a Milgard. It's not a thermally broken window. It's just a, you know, UPVC window. The inside temperature of the mullion of the window is 96 degrees, even though it's 70 degrees outside. So it's a beautiful, sunny Central Coast, San Luis Obispo day to go sit outside on your porch. My brand new apartment is a bread oven in the afternoon. So after about 2:30, 3 o'clock, you can't be inside the apartment. It just cooks. So it's just to show that sun control is needed for many different reasons. It's not just for ambient lighting. That temperature then affects all the other temperatures of things inside my apartment. So my couch gets really warm. My kitchen countertop fluctuates from 90 degrees to 40 degrees on a daily basis because it's attached to the same wall as that window.
So we're talking multiple layers here of, yes, it's easy to take a home, a new construction and even existing, convert it to all electric, but part of that whole package that makes it easy is then you also have to go around and look at what's reasonable for the fenestration, because we want to control those temperatures. So in Mike's case, being allowed to put those exterior drop shades would solve that problem for an existing structure. And in new construction, we say, hey, strategically place the windows. So part of that too is having continuous exterior insulation to eliminate that same thermal bridging you saw in the window to happen at every stud in the project. Now the new code up the ante on the U factor for walls and windows. And so even a 2x4 wall with an R15 cavity would still require an equivalent R4 exterior continuous insulation on it for climate zones 6 and 7. That's Santa Barbara, Ventura, even mild. And then up here where we are in San Luis, Atascadero, climate zones 1 through 5 and 8 through 16, we're looking at a 2x6 wall with R21 with an R5 continuous. So even if you have a project that mitigates away from the exterior continuous, which we don't recommend, that's still what you're going to be compared to for baseline. But it's also going to affect comfort. So part of this all electric moving to lower carbon footprint is to also improve comfort and to let those all electric equipment heat and cool your home in an efficient way. Now, adding the exterior insulation is actually the recipe is pretty straightforward. If you're doing wood construction, you build your stud walls, you fill the cavities, you add your structural sheathing, then you layer on your house membrane that is sealed at the bottom and the top, as well as the seams and all that in the middle on your membrane. So we want to seal it at the foundation, seal it up at the top plates into the roof, add the continuous rigid insulation, and then create a drainage plane through some kind of furring strips and your exterior finish.
And it's important to note that this is, you know, there is no one panacea. We're not giving you a detail and saying, hey, do this detail, problem solved. Like, you can still be wildly creative as architects and come up with anything that works. You do not have to use this sample. So this is one way of doing it. I have done this way. Don't want to like pat myself on the back, but pretty successfully. But I've also done other ways with different systems that have worked just as well. So these are two projects of mine that are on the screen right now. This one up in the left-hand corner is in town here. And this one is from a renovation, actually a deep energy retrofit in Los Angeles of an existing masonry building that I did. So in this example, I'm using a wood fiber board that has paraffin wax in the board itself. So it actually repels water off of the boards. You can see it in action if you're ever coming through town and want to check it out. You can put a hose on it. We just got 11 inches of rain in 2 days, and that wood, I put a moisture meter on it. 24 hours later, the wood fiber board was totally dry. We had rain 17 feet inside our building. So the slab stayed wet for 3 or 4 days. The wood fiber board on the outside dried almost immediately. So this same company makes another product in this line where you would do the system that Jennifer just showed, and you'd have a second weather protection layer over the outside of the insulation. So there are different ways of doing it. We recommend staying within a brand manufacturer product line. This stuff is from Gutex, which is a wood fiber board manufacturer. There's a company, there's an American company coming online soon. I think they're called Go Lab from Maine, who will be introducing wood fiber board made from wood sourced from furniture factories in America, which is really exciting. I got this stuff from shipped over from Germany. Find the trades to do the installation. I did this myself with a 24-year-old architect, graduate employee, female employee who's amazing. The two of us kind of just rocked this out in a couple days. It is not hard to do. And we just did all the detailing ourselves, did the drainage planes ourselves. It's really no different than thinking about sheathing. You don't want your wood sheathing to get wet. Well, you don't want bulk water to hit it. Think about it with your exterior insulation as well. You're just adding another layer. Builders can figure it out. I really recommend on-site mock-ups. So I don't know if there are architects and builders in this room, but this is a great opportunity for architects to actually get your hands dirty. Sorry, that sounds demeaning. Not to actually get your hands dirty for once, but there's an opportunity to kind of, put some stuff together. And when you physically put it together, it's a lot different than doing it in a drawing or on SketchUp or CAD or Revit. You can physically see, okay, how is a raindrop? How do I think like a raindrop on this? How is this going to maneuver outside my assembly and keep this assembly dry? That word dry then ties into what kind of materials you're using. You have to think about building assemblies that have the opportunity to dry, have the capacity to dry, or if you're building assemblies that don't have that capacity, you really need to bulletproof those assemblies. So I tend to take an Occam's razor approach to things and try to keep it simple. So I use wood fiber and I use cellulose in my walls. And that's kind of been my approach for a while. But, everyone's different. Every day is a school day.
So Mike and Jen, before I move on to the next topic, there was a question on the chat from Peggy. Peggy, do you want to unmute and just go ahead and ask it? I don't know if she's got her mic up and running.
Yeah, I had coffee in my mouth. Yeah, I was just wondering, continuous insulation, is it still required on, like if you're using SIPs? I think for my own house, we're using SIPs, and I think the Title 24 we were okay without the CI, but are you saying the continuous installation is still a good thing, especially on south facing? I mean, we got a huge south facing elevation, so.
Peggy, do you know what kind of spline system is being used on your SIPs?
I don't know.
That's exactly what I was gonna ask.
Yeah, okay,
Yeah,
because see,
okay, I'll
that
check.
it's kind
Yeah.
of like do you know, they say like the devil in the details, because some SIPs are put together, they're 4-foot wide panels, but on the edge of each panel is a stud, a 2x stud, and then they're putting two 2x studs together. So you actually get a lot of thermal bridging, just the same amount as if those studs were separated every 24 inches, right? It's the same number of studs. So you might need to do something if you want it to perform as well as what we're talking about. However, if it's just, some of them don't have those splines, or some of them just have like a little strip of OSB as the spline to hook it together. So a lot of it kind of depends on how it's made, but we can address that a little bit more after.
Some SIP wall panels too, Peggy, you'd frame the house typically. I don't know if you're timber framing or if you're using conventional
No,
stick
timber.
framing. You're timber framing?
No, not. I
Just
wish.
stick framing.
Yeah.
Yeah, sometimes
That's
SIP panels,
It's SIP
Yeah.
framing, yeah.
yeah, and sometimes the SIP panels come with like a tongue and groove in the foam. So you're kind of locking the T and G together of the foam, and that would be continuing the insulation layer without any thermal
Gotcha.
bridging. So it kind of
Yeah.
depends on what
Yeah,
you're using.
I'll check the details and I'll get in touch with you.
Cool.
Okay.
All right. Thanks.
Thank you.
And then just to let
Here.
everybody know on the call, we're coming up just on about 9:53. We're gonna complete this last section of the presentation, and then we are planning to leave time for questions afterwards. So if you've been holding on to your question, now is the time to get it in that chat. We will be shifting to just a question and answer mode after this next module is presented. And I'm collecting the questions, and I'll sort of present them to the speakers afterwards live.
We have about 12, 13 slides to get through, so we'll
Perfect.
Okay.
do it.
I'm going to touch a little bit on the fourth part of sort of how to package all this together. So we've got heat pumps, continuous insulation or real better envelope, reasonable fenestration, part of that well-designed envelope. And then now we can add our renewable energy for our whole all electric package. And kind of reminder, PVs are required for low-rise residential new construction only, and the other is just solar ready. When you're designing the house, you want to, and I'm talking to mostly the designers here to say, hey, you should accommodate the space for the PVs in your design as part of one of the programmatic requirements right off the bat. It'll simplify your life and it'll simplify the builder's life for sure. And so orientation anywhere from south-southeast to due west are perfect for PVs. Avoid, unsupported roof structures, obviously for the architects and engineers here. You want to avoid shading from chimneys or other buildings or trees or parapets. And the rule of thumb is to take back the PVs 2 times the height of that obstruction. Residential code says you need 3-foot aisles. It's on valleys, it's okay to split it, 18 inches on either side, but typically the fire code's asking for 3 foot off the ridges, 3 foot off the eaves on the side, and for non-res 6 feet. And that means 4 foot around also skylights and 4 foot around the roof hatches for the non-res buildings.
I have a question, Jennifer. Let's say you're putting your PV panels on a flat roof,
Yes,
residential.
yes.
Do you need 1 3-foot alleyway access, or do you need 3 feet around the whole entire system?
depends on how big, and you're probably going to want to bring it up with the authority having jurisdiction with and the fire chief. We have seen projects where they required or wanted only 3 foot on 2 sides of like a garage, you know, a garage with a more or less flat roof. They really wanted to make sure they had good access on 2 sides. So that's where they could put the ladders and they could get from one roof to the other roof. But if they can't get across your roofs, then you might have to add another alley walkway so they could go from one roof to the other.
Cool.
And architects, this is for you to give you an idea of what that prescriptive requirement is. Kind of, you can show your PV's performance through your time way, but you can also do it prescriptively. And if you were to do it prescriptively to get an idea of how much space you need, you would use this formula that takes into account certain factors based on climate zones. So the CZ column on the left is your climate zone. So let's say we're going to take a look at climate zone 4 in Atascadero, where I am, and I have a 2,000 square foot home. I'm going to take that 2,000 square feet, multiply it times that A factor, divide it by 1,000, plus I'm going to add, this is 1 dwelling unit, plus the B factor of the 1.21, and I come up with a 2.38 kilowatt DC nominal system size. So what does that mean? Okay, next slide. What that means is you can, rule of thumb, say you're going to use a panel that's approximately 67 by 40 inches. That's kind of a typical size panel. It's going to produce about 350 watts DC. It could be 380, it might be down to 320, but usually if you took 350 as a rule of thumb or took the lower end and said 320 watts, you could take your 2.38 kilowatt size you need and divide it by the 320 watt of the panel times 1,000, and that's going to equal 7.4 panels, but you got to round up. You can't have fractions of panels. So 8 panels is what you need to size for, and each panel being about 67 by 40 inches, that's your prescriptive size. Now, if you knew the project wanted to be ZNE and you were not carefully articulating all the appliances and the use load, et cetera, but looking at a typical family, you'd add about another 60% for ZNE, and you'd add another 4 to 7 panels for your electric vehicle charging. Again, that EV charging size, that totally depends on how many miles you drive and if you're charging only at home or you're charging away from home. But that would give you an idea of the size you would need for estimating the PVs for your clients. Okay, now we're going to touch on some design considerations to keep in mind, but like Mike pointed out, we actually have other classes that go way more into detail on what balanced ventilation is about, on what heat pump water heaters require, what you need for heat pump space conditioning. But I want to hit on those quickly and then give you a little bit more information on the space you want to accommodate for inverters and batteries as you look to moving towards all electric. And please stay tuned for the little section that Mike's going to do on induction cooking, because that's, we've got a video and we're going to show you how fast induction is compared to gas.
So it's 10 o'clock, so we'll go through these additional design considerations. We'll try to go through them quickly. So all of this system we have in our minds that we're bringing balanced ventilation into this house, residence, multifamily. So the couple ways that we do that, There are ducted ventilation systems and ductless ventilation systems. All of these are very efficient, low energy usage systems. So we're building a tighter house where we don't have gas inside the house. You might not have a gigantic kitchen hood, a kitchen range hood if you're going to use induction cooking. So we're bringing fresh air into this tighter home and exhausting stale air out of the home. And it's just a continuous cycle. So a ducted system. And this isn't unlike the concealed duct heat pumps. It's a ducted system because we have some tubes moving air through the building, but it's not ducted like your typical gas FAU. So this is actually a Zender that I've installed, and this is the kitchen. And these are just 3-inch ducts running off of an exhaust fan that's in my kitchen. So I keep it about 6 feet away from my range hood. We will never need a kitchen hood. We are required by code to have a dedicated kitchen exhaust fan. So we're actually going to be putting essentially a 290 CFM bathroom fan in, and the clients will never turn it on, but we're required to have something. So the Zender will actually do all of the removal of the stale air from a kitchen. So Zender makes a ducted system. Panasonic makes a ducted system. Renson makes a ducted system. The Zender is kind of the Cadillac, and what would be, it's almost, that word is almost used in place of HRV. People will ask for a Zender system like you'd ask for a Kleenex. Ductless is a Lunos system. I think Lunos is the only ductless through wall system that I know of. So this is one I installed on the, this is a passive house retrofit in Los Angeles. It's basically the size of a coffee can. And it has a ceramic core that recovers the heat inside that tube. And that is what it looks like on the inside of the house. It looks, I don't know, 6 by 6. On the outside, it looks like a dryer fan. So.
Okay, there's some design considerations for the integrated heat pump water heater. We will be going over this in a lot of detail in another class, but I want to hit on a couple of things in case you're not familiar with these appliances. You can get them now at like Home Depot and Lowe's. They're taller than a standard gas or electric tank because they've got the heat pump on the top of the unit. They're about as noisy as a refrigerator. And one thing you should be aware of is because they are pulling air in through the unit, typically through the top, running that air past the condensing coils, what you're going to have coming out of the unit is cold air that's been dehumidified. So it's important to know that as you're working with your clients, because if dumping cold air into a particular part of a house or someplace in your project is a problem, there are ducted and powered vet kits available that would allow you to pull air from the outside and exhaust that cold air back to the outside instead of into your house. There's the sand and split system type, which Mike mentioned. Again, we've got another class coming up that'll go into this in more detail, but to give you an idea of what your options are, this is something that works great for multifamily. It's also good for single family applications. That outdoor compressor with its electrical connection sits outside the house on a simple pad, and then you've got a completely quiet, noiseless, no electrical moving parts tank on the inside of the house, and you can separate those between 25 and 50 feet depending on the system, and that way you can put that hot water tank right at the plumbing fixtures that you are using. So you can put that right where you need it for your showers and your laundry, and no recirc pump needed, and you have hot water right when you need it.
We're actually installing ours in the laundry room right next to the washing machine. So.
Yeah. Yes. And another thing to keep in mind is that these outdoor units, whether it's for heating hot water, like in this multifamily example on the left, or used for space conditioning, like the example of the outdoor unit on the right, you've got to make sure you maintain clearances around these outdoor units and make sure they are free and clear of potential sources of debris, like dryer vents, which can clog up the fine fins on these that allow the heat exchanger to come, because they do pull air in and around on one side of the unit and push the air with the fan through the front of the unit. So like Mike likes to say, you wouldn't want to, how do you say that?
You wouldn't turn a fan on in front of a pile of sawdust and expect it to operate properly.
Right, so same thing with those. Okay, and then, you know, what we hear coming up a lot for our clients when they are looking towards all electric is they're also thinking it's going to be more resilient with power outages if they have battery backup as part of it. So if you're going to talk to your clients about that, some of the things you should know is that you can set up the battery to power up critical loads inside the house or the building. It can very much be a part of your zero net energy strategy. There is Title 24 credit for the batteries. And it's a great way to add to grid stabilization and kind of take the peak off of when your PVs are producing the most amount of energy in the middle of the day. You may not be using all the energy right then and there, and you can store that into your battery to use later. And to give you an idea of how much space it takes, you want to, that example on the previous slide was an exterior example. However, we're a big advocate for putting all of this on a protected, weatherized inside space, like the inside wall of a garage. And if the client doesn't want all this equipment now, we say as architects and builders to go ahead and designate up to a 10-foot wide area in the garage where a battery can be mounted. We say, if you got your PV system and you're going to put your inverter there, we say, put your inverter there, take care of your load center and your disconnect. But then if you're going with the battery, make space for all of it, including EV charger. And, you know, it only needs about 10 feet wide. You can squeeze it down a little more and make it go taller than the 6.5. But if you had 6.5 by 10 feet wide, you'd be set for all of that.
So now we're going to wrap this up with kind of the biggest hot button topic of all that could probably have hours worth of banter and conversation. Electric cooking seems to be one of the biggest roadblocks to going all electric and not having gas inside the home. So we're not talking about, you know, electric resistance. We're definitely not talking about those little tiny, whatever those things, you know, typical old school apartment oven range. God, those things, I burned enough members only jackets on those things as a kid to, yeah, my mother's got a lifetime of memories. But we're talking about this kind of stuff. So, you know, induction cooking is, I don't understand the bad rap. Wolf, Sub-Zero, Viking, all of these companies are shifting their ranges to Sub-Zero. They'll still make the gas ones, but if you want to spend $13,000 on a range, they also make a $13,000 induction range. So you can lighten your wallet the same way and get a much better piece of equipment without having methane pouring into your house as well. So we're talking about systems like this, these nice glass tops on a countertop. I like that they show a Le Creuset pan here. That's a pot. I'm not a cooking enthusiast, so that's a pot. Because a big argument is often that people can't keep their pots and pans. Well, you can buy a set of induction pans off Amazon for $199. Le Creuset, which a Le Creuset coffee mug is like $199, but all the Le Creuset pots and pans that people keep as heirloom products, they work with induction. Cast iron works on induction. The control of induction, we think we can control things with flame because we watch cooking shows with flames. It's actually much more intricate with induction. So you can actually melt chocolate in the pan to the exact consistency that you want it without burning it. So again, people often think that they're more efficient cooking with flames. They think more flame, more heat is more efficiency. And that's not how it works. You're losing most of your efficiency on a gas cooktop. It's not going to the destination. So it's coming from the source and going around the destination. Whereas with the induction cooktop, you can see that it's 84% efficient. So what's coming from your source is going right to your destination exactly. And then to wrap it all up, I hope this works. Quick little video just to show you it is not faster. This is like the grand finale of a 1-minute video.
Mike, didn't you show this video to an engineering client of yours? And then he was like, okay, my wife can have induction.
All right, there you go. So we don't need to watch the whole thing, but God, YouTube, a source for 10-year-olds and a source for 44-year-olds as well. I actually used that exact video working with a client in San Diego who was really close to going to an all-electric retrofit of his house, and he didn't want to get rid of his gas stove. And he is an aerospace engineer, and he actually said, "Look, it's just faster for me with a gas stove. You know, we want a Wolf gas stove." And we pulled that video up in the office with him, put it in front of him, and he watched it, and he said, "I'm an engineer. I see the proof. I like the data. I'll go with it." And so he switched, and that was all that it took. So anyway, that is it.
Okay, we think it's easier to go all electric, and we suggest that when you talk to your clients, you just the facts, no myths, show them the data, give them some choices and options, and then we recommend you take the classes on the heat pump space heating and the heat pump water heaters if you're not familiar with those, so that you can talk to your clients about it. And continue to move forward on part of California moving to a reduced carbon footprint way of building. And with that, we want to open it up to questions. I think Michelle's going to monitor the chat, and Erica's going to pull up a poll for an evaluation. And Mike and I will stay on the line as long as you want and have questions and discussion for us.
Thanks, Jen. So Erica, can you put up the survey? Great. So we invite everybody to stay on the line, and we will be going through questions. If you could fill the survey either now or before you leave the presentation, that would be fabulous. It really helps get some feedback to us and to 3C Ren in terms of what you've learned, what works for you, what you might want to see in the future. We would really appreciate that. I'm going to dive right in with a question that came up while we were talking about batteries, everybody. It's from Brendan, and I'm assuming Brendan is still on the line. Let me see. Brendan, do you want to unmute and ask the question yourself?
Hi, all. Can you hear me?
Yes, we can.
Oh, this is great. I'm really glad to be here. I'm brand new to the home building industry here in San Luis Obispo. So this has been very informational, and I'm very glad to be here. Yeah, I noticed it was great because after I presented the question in the chat, a depiction of a Tesla Powerwall, I believe, came up. And I know that although it may not be part of a true passive house system to have a battery backup and not to use petrochemical products, I do know that lithium ion batteries, which are typically used in these battery backup systems in a residential usage, curious to know if there's an alternative to the lithium ion battery for this battery backup system, and if it's even fully necessary in a passive house situation?
Good question. Jennifer will probably have the answer to the first one. For the second part, specifically talking about, passive house, which is a whole nother concept. The goal of a house like that is to reduce the loads of the home to almost nothing so that it operates without any sort of equipment. So a battery backup system is still a good idea. And in many cases, it's used just to operate a few parts of the house. So you might have a battery where you might have a battery backup where if the power goes out, that battery is connected to just the kitchen, maybe the refrigerator, maybe the induction cooktop, and maybe a few lights. So you can size the battery to only operate certain aspects of the house, or you can size the battery to operate the whole entire home for 4 or 5 days. So you can choose what you want to do with the size of the battery.
Yeah, and for part of the other question, so for some of our projects that are completely, let me start over. For our projects that connected to the energy grid, what most of us do, have been doing for a long time, even if we get PV panels on associated with our home or our building, commercial building, we in essence use the energy grid as the battery. So you produce electricity through your PV panels when the sun is shining, and that energy, if it doesn't get used directly into your building, it goes into the energy grid and gets used someplace else. And then we essentially at night expect the grid to give us energy back when we need it for our buildings. So some folks want to make their home, their project more resilient, and they don't want to have to rely on the grid in case the power goes out. Maybe their family they're diabetic and they want to make sure at least one refrigerator keeps going that has their medicine in case of a power outage. So they might use a battery. You could use like a Tesla Powerwall, you could use it. Simplified battery system, there's Sonnet batteries out there, but you can also, like kind of the old school off-grid projects that I used to work on, we didn't have those type of batteries at all, and we used batteries that were completely recyclable, batteries that maybe didn't store as much energy, so they just took up a lot more space, and you'd have to go and maintain them and make sure that they have the levels, their water levels in the batteries and keep it up. But those batteries are completely recyclable. Now, with the contemporary batteries, the battery technology is such that they're trying to get away from depending so much on lithium and looking at being able to recycle them and have a life. Those batteries have a life after you use them in your house. So I'm happy that you're thinking about that full circle. We just happen to use that line of products to show how much space it would take for one of the more modern systems. But you could go with a more space intensive, older, different type of battery.
We've got another question from D. Carawan. Do you want to just unmute D and ask your questions about gas versus electric utilities?
Oh, can you hear me okay?
Yeah.
So I'm an architect. I do a lot of remodels. And when I'm asking clients to consider swapping out, replacing their gas appliances with electric, and one of the big questions I always get is the cost to run those electric versus gas appliances. So is there anywhere to find data on how I can help convince clients that it's going to be reasonable?
Yes, and I cannot give you the websites right off the top of my head. Mostly what it is right now is me connecting you to the folks who've done the research as part of the CEC and the case studies. So what we're going to do, that's my dog Sparky, everybody. Okay, what we're going to do is teach a couple of more classes where we're going to connect you with this information specifically. But what the research is showing right now is that with the current cost of electricity and the current cost of gas in our area, that for heat pump water heaters, for example, those two things are going to be on par with the amount of water that you use for your heat pump water heater and for your gas, like on demand unit. The gas right now is slightly less expensive, but when I say slightly less expensive than running the electric heat pump, we're talking about the current rate structure, and we're talking like $20 out of the whole year, slightly less expensive. So, I mean, when you talk to like an engineering kind of number nerds, I'm like, oh, well, you know, the facts are the facts. But when you talk practically to your clients, I mean, they're going to spend 20 bucks on a couple of coffees and a little snack at the Starbucks like that. You know, they're not going to notice the difference in the cost on their appliances. Similar thing with the cooking and on the space heating, both Mike and I have personal examples plus the numbers. I switched my house off of gas for the space heating and went to the mini splits for both heating and cooling. And I am spending more money on the electricity, but I didn't spend any money on cooling. And my utility bills have only gone up for a few $100s for the whole year. And so that couple $100s for the whole year, as opposed to $40 on my gas for the heating. So yes, I am spending some on air conditioning, but my house is 1,200 square feet, a couple $100s for the year, and now I have air conditioning. Yeah, it's worth it. And, you know, I spend more than a couple $100s a month on feeding my kids food. So it's, you know, that gives you like an order of magnitude, I think, what costs we're talking about.
And
Right.
Dave, we usually say that if you're working with clients and they're going through a renovation or a remodel, and I did a lot of renovations and remodels back east of this sort. We recommend that if you can keep, if they have gas and the units are still in really good shape, you know, maybe they're a couple of years old and now they've decided to do a renovation, which happens all the time. If you're not going to spend the money to change out that system, spend a little tiny percentage of that money and get it ready for the system to just be taken out in a few years and the next electric one put in. So add some conduit, add some chases for electricity, and then that's part of the future proofing aspect. So at least you can have that conversation with your clients. Well, if you don't want to spend X amount right now, let's think about when you're going to have to change this out in 5, 7, or 10 years, and let's spend a little bit now and get it ready. So when that time comes, it's just a 1-for-1.
Great.
So.
Mhm.
That's all the questions that we've got on the chat, and we're sitting at about 10:25. So I did want to let people know that we remain available. You know, we can always be contacted. I guess Jen usually puts our emails up. Jen, do you want to put our email addresses up if people have questions after the webinar? We wanted to thank 3C Ren for helping host the event today and let people jump off and go about their workday if they need to. We do have about 5 more minutes if people want to stay on and add some more questions to the chat. I will be here to moderate, but we did want to say thank you and give people a moment to jump off, fill out your survey, let us know, you know, what went good, bad, and otherwise. And we look forward to seeing you all on our next webinars. Do we have a slide with future offerings?
Yes,
We
Eric,
do,
I was
yeah.
going to say that. Erica's got a slide for some things that are coming up.
All
Erica,
right.
do you want to take these slides? Go ahead.
Very quickly. Okay, I see several people submitted their AIA numbers, so those credits will be processed. But if you have any questions, contact Itzel, whose email address is right here. We will also be sending another survey. If you want to provide written anonymous feedback, you're welcome to do that. Upcoming courses. So we have Passive House Retrofits. I believe that's a half-day course, right, Sean, on March 2nd?
Correct.
Thank you, Sean. The Building Blocks of Passive House Performance on March 16th. That's more of an intro. Well, they're both intro courses, but that's a shorter course. And then we have HRV and ERV for Passive House applications on March 30th. And then to really round out our Passive House series, we're doing the Passive House certification course for designers and consultants. 3C-REN is covering the cost of this, everything except for the exam. So it's a really great opportunity if you've wanted to do Passive House, but the cost is a bit of a barrier. So if you live in the Tri-County region, please check out our website. All of this is at 3c-ren.org/events, and you can find all of the links to get registered.
I would really recommend anybody who has the opportunity to take that Passive House certification course, take it. I've done both FIAS and PHI, so Passive House Institute US and Passive House International. I've done both courses. I did the first one in early 2015. I did FIAS after I'd already built to that level. And it's just, I don't know, I think it's one of the best things I've ever done in my career. Once you learn that kind of stuff, there's no way to unlearn it. And it's just going to help you think about designing and building better buildings all around. So even if you don't get certified, take the course.
And so Erica, you're saying that all these events are available on the 3C-REN calendar, correct? And the registration links are there.
Yep.
Okay.
Thanks, Michelle.
Great. All right, why don't I let everybody just go. We want to thank you again for joining us today. You can always contact us at the emails on the chat here. We'd love to field questions, and we hope to see you on a future webinar.
Thanks, everyone.